All right, so let's go ahead and talk through some of the information necessary to complete Lab 5. In this lab, we're going to be focusing on torque and then balancing torque to look for missing information. So torque in general, because it starts with the letter T, and so do several other things, we have the Greek letter tau. So TAU, which just basically looks like a letter T, but it's Greek, so it's kind of fancy looking. This is going to be the radius, or sometimes L for leverage, of the lever arm or torque arm multiplied by whatever force is there. So if you want to increase torque, if you've got a constant radius, then you'll need more force. If you have a constant force, you'll need more or bigger radius. Then if we combine this with other torques, if we want to achieve balance or equilibrium, then whatever torque we have going in one direction has to be equal and opposite to the torque going in another direction. If you have too much clockwise torque, then obviously it'll turn and go clockwise. If you have too much counterclockwise torque, then it'll turn and go counterclockwise. The only way it can hang in balance is if they're the same. Now, we do need to be careful on the wording here a bit. We don't typically want to say that things would just fall down in this case because they're tied off with a physical pivot point or fulcrum. If they don't balance, they're going to rotate around that pivot point. Okay, so, I suppose we can squeeze it in here. It's kind of a setup zero that we want to talk about first. So if we draw a meter stick, and just straight line, simplest version of what I can draw, and say that it has a mass that comes down, and I'm going to be very unoriginal with this. Let's say that it's 123.45 grams. Then you probably know already that if I want to support this, if I don't want to do anything else, if I just want to hold it by, say, tying a string or putting my finger underneath it, and I want to hold it in place with one force and nothing else going on, then I'm going to have to hold that under the middle of the meter stick, which just happens to be because a meter stick, remember, 1 meter is 100 centimeters, then the middle of it's going to be 50. Now, the reason this works is because then the mass of the meter stick itself is directly at the pivot point, has zero leverage or zero radius, and therefore makes zero torque. So that's the reason why it works that way. If we have a meter stick and we hold it in a different spot, so say this is my meter stick, again, the mass is going to average out to be in the middle, so 123.45 grams. That's going to be at 50 still, because any reasonably well-made meter stick will have the center of gravity at the middle. But let's say now that I take the string and I move it over slightly. I put it here. And again, I'm not going to try very hard on these numbers. We're just going to count. So let's say that this is at 34.56 centimeters. What's going to happen is that there's a pivot point here, but there's actually something away from the pivot point, something that has leverage. So we talk about R, we mean the distance from here to here. And what that's going to do is cause this to turn down in that direction. So it's going to create torque. In proper units, torque needs to be in newtons and meters, but in improper units, let's just kind of set up and see where this is going at first. So I'm going to say torque, and I'm going to put it in parentheses because it's really not quite proper. Technically, this is supposed to be radius times force like we saw above, but I'm going to say radius times mass, and again, know that this isn't quite proper torque. So that radius, that distance there, we want to use something called relative position. We need to avoid absolute positions here. So it doesn't matter currently, or at least in my formula, it's not important that the mass is at 50 centimeters or the string is at 34.56. What is important to me is how far apart those things are from each other. So I want the difference. Look at where the R is drawn in the picture. I want the difference between these. We're going to assume that the meter stick is well made enough that the center of gravity is going to be exactly at 50. And that's going to be important for significant digits, which we're not going to look at too much today, but it is going to control some of how the rounding happens later. All right, and then the mass that's here, again, this is improper because normally we should be changing the units, but we can use this to work down and get some kind of answer for this part so far. All right, so again, our improper torque. If we find this difference, then we're going to have 15.44 centimeters. That's going to multiply by the mass that's hanging there, and basically 2, 3, and apparently I can't count. So let me fix these. Yeah, evidently counting is the hard part of this question. So 1, 2, 3 points. Oh, now I can't get my colors right. There we go. 123.45 grams. All right, better. All right, but here, 123.45 grams. Okay, then multiplying these things together and rounding to 4 significant digits, because that's the one that's holding me back, this is going to give me roughly 1,906, and then the odd units here are going to be grams times centimeters. So that's the amount of torque, or again, a torque-like measurement that I'd have to balance in the other direction if I wanted this thing to sit in place. To see how this relates to our normal numbers that we'd want to use for torque, we can take and convert this. So notice I didn't put the quotes on it this time, but I can take 1,906 grams times centimeters, to stick that over 1, and I can chain together our conversions. So a couple of different ways that we can set this up to streamline things slightly. We want to remember that a kilogram is 1,000 grams. But I'm not going to put 1 kilogram on top, because then we have to take a kilogram and convert it into newtons. If we assume that we're on Earth at roughly sea level like we normally are, then we can sort of chain that together. 1,000 grams technically turns into a kilogram. The kilogram turns into 9.8 newtons. So by the transitive property from geometry way back when, we can say that these two things are equal to each other. Okay, and then also we need to remember that 100 centimeters make 1 meter. Looking at our units and making sure everything cancels the way that we expect. Grams cancel grams, centimeters cancel centimeters, and we get newtons times meters. Okay, so taking that number and multiplying by 9.8, and then dividing it by 100, and then dividing that by 1,000 is going to give us approximately 0.1868 newtons times meters. So you can see the units are vastly different from each other. Now, a nice thing is going to happen because we're balancing torques with most of these questions. So up here, notice that clockwise torque is equal to counterclockwise torque. Then even if we do go through the steps and we convert everything into proper torques, those conversions are pretty much going to cancel each other out, because they would have needed to happen with each different set of grams and each different set of centimeters. And so with a single pivot point, you can use just about whatever units you want, as long as they actually measure the stuff you're talking about. So like, you can't measure mass in seconds, because that won't make sense. But you can measure mass in grams or kilograms. You could technically use pounds here if you wanted to, and this equation would still work. Okay, so let's use that information. Again, what we just looked at is kind of like a setup 0, if you will. So if we move on to setup 1, and if we were to follow the instructions here, we're going to take a 100-gram mass, put it at a certain spot. The very first thing we probably want to do is draw this all, so that we can see what's going on. All right, so we're going to draw the meter stick first, and then basically before we do anything else, we want to make sure that we remember that it has a center of gravity in the middle, so the mass is going to average to be the middle. All right, so here's my meter stick, and then the very first thing, we'll draw a line down. Now for right now, we're pretending we don't know what this mass is, so just M, and that's a little s for mass of the stick. And assuming it's a reasonably well-made meter stick, then this is going to happen at 50. Okay, and then it tells us that we're going to put a 100-gram mass in another position. So this one's going to go at the 20 centimeter mark. Okay, and so I hope it makes sense. I'm going to draw a couple of things that are wrong first. But let's say that I try to put my string over here to balance everything, then notice that all my torques are going to go around in that direction, and there's no chance that it was ever going to balance. Likewise, if I try to put my string somewhere over here and make that pull up, then everything's trying to go around in this direction, and they're working together. There's no chance that they were ever going to balance each other. So the string's going to have to go somewhere in the middle. And that way, you have one torque. Suppose we can code these. You have one torque going around this way, and then you have another torque going around this way. And if we can find those, we can set them equal to each other, and we can solve some stuff. So for our example, just to make nice numbers, let's say that this string ended up at exactly 40 centimeters. We're not going to really worry about significant digits anymore, just because different groups and different types of meter sticks made of different materials can get all sorts of numbers, and then the significant digits will change technically between group to group. So we'll just kind of run the numbers and learn the process here. Okay, so in the one direction, and again, we're going to use the improper torque because the conversions would cancel each other anyway. Then I'm looking at my relative position. I've got my string at 40, and then I've got a mass hanging at 20. And so I want to know how far apart those are so I can see the leverage that this mass has when it's trying to turn down in that direction. Then the mass that's there in particular is going to be the last thing that contributes towards that torque. Okay, so finding the difference, this is going to be 20 centimeters, and then the other part is 100 grams. And this isn't proper torque, but we can multiply those together. We can get a torque-like measurement of, in this case, 2,000 grams times centimeters. Okay, so in the other direction, we want to do a similar thing. We want to look at the relative position. How far apart are these things? Not exactly where do they sit now. So 50 centimeters minus 40 centimeters, that's the important part. And then multiplying by the mass of the stick, which as of right now, we don't know. I was trying to calculate first. Okay, so 10 centimeters is the difference there. That's the leverage that this has because it's off center. And then multiplied by the mass that we don't know. And we can't do anything else with that. So in this case, we just want to bring it down and we want to set it equal to the other part. And that's going to give us our way to go back and solve for missing information. Now, one thing I want to point out here, a lot of times students will make this mistake because again, they look at the absolute positions and not the relative positions. But the answer we're going to get here does not happen because the 40 and the 20 here are half or double, depending on which way you look at it. The reason this happens is because the 10 from going in this direction and the 20 going in this direction are half and double from each other. So in the end, we're going to get an answer that you may have seen coming, but 2,000 divided by 10 is going to give us 200. So we get 200 grams. So because of the fact that the smaller mass is twice as far away from the string compared to where the mass of the stick sits, then the 100 grams gets doubled and balances with a 200 gram meter stick. Okay, and so we're going to follow through with that trend. We're going to use 200 gram meter sticks on the other questions as well, just to be consistent, to use nice numbers so we can learn the process. In the next one, we're going to move stuff around a little bit. Eventually I'll get there. But the first part is still exactly the same. We're going to want to draw a meter stick. I always draw the center of mass first because this is the main part that students will forget when they get stuck. They'll draw a picture and try to set up a formula. And if they are missing information, it's usually this part, because you don't physically see anything for it the way you would if you were to build the other setups. Okay, then now reading the directions a little bit further, at the 25 centimeter mark, so halfway from 0 to 50, we have a 100 gram mass. Okay, and then we have a string tied at 60. So the string is tied here. Now, relative to the example I gave earlier, whenever we were holding the meter stick off center and we weren't doing any other forces or masses hanging there, then if you only have torque in one direction, then things are going to go in that direction. So if I'm looking this way and I don't read the rest of the question yet, then there's no chance that this was ever going to balance, because these two things are both going to make torque. And again, that's torque. That's going to work together and try to turn even more in the same direction. So let's set up and see if we can find that number so far, and then use that to finish solving whatever's left over. So if we go from left to right, thinking from 0 to 100, then the first object that's there is sitting at the 25 centimeter mark. But remember, you want to think of relative positions. So 25 centimeters needs to be taken away from the string position so that we can find out how much leverage it has, and we need to pay attention to what's hanging there. And plus sign, these torques are working with each other. This other one compares to the 60 where the string is, but this is the mass that averages at 50. And then the mass that's hanging there is the full mass of the stick, because that's how the center of gravity works, and that's going to be 200. So this thing we can simplify down a fair bit. We can find each of these relative positions by subtracting through and finding these differences. So we get 35 and 10 centimeters respectively, multiplied by their masses, and that's going to give us individual torque type measurements for these. The first one works itself out to be 3,500 grams times centimeters, and the second one works out to be 2,000 grams times centimeters. So working together, these things combined will give us 5,500 grams times centimeters. And whatever torque is made there has to be balanced out by a torque that happens equal and opposite. So there's no way that it can still be turning in the same direction. I need to somehow have that amount of torque going the other way. And that's where, if we read the last part of the question, we can figure out what's going on. We have a 300 gram mass that has to go somewhere. And as it turns out, that's going to need to be over here so that we can balance that part out. So 300 grams. We don't know where that's going to need to go. So for right now, we'll just draw in and we'll call that R. Which makes this side actually very simple. R is that relative position, because that's how the formula works, multiplied by the 300 grams that are hanging there. And that doesn't simplify or do anything. So that's really just going to come down and come into my formula. All right, then as far as the units, we can take and cancel the grams first, as long as you do it at some point, but we can do it now to have less to write down. We would divide by 300 in order to work this down to R, and then we get that R is 18 1/3, so 18.33 centimeters. Okay, now we have to be careful with this information because this is a relative position. If we were to try to look on the meter stick and see where this was going to be, then that would have been somewhere like over here, which is very clearly wrong. So we need to keep in mind that we're looking for something that's way on down from the end. So to find this position, we have to keep in mind that the way that we drew R is only coming over from just where the string is. So to get this to be a position, we have to add that reference point and get an absolute position. So we're going to add 60 centimeters to this, and it's going to be 78.33. A lot of times in the hands-on labs for those sections, students will find that first number and then do the percent error on it early, and then you get something like 40% or even 80 or 90%, depending on the meter stick and the material and the different measurements. And it looks completely wrong, and that's because, well, technically it is, because relative position and absolute position are usually not going to be the same number, at least with the way that we've set these up. So something we'll have to pay attention to. Our first answer that we calculate is 18.33 centimeters, but then we have to adjust that for the fact that that's just starting from where the string is at 60 and then coming over from there. Okay, and that brings us to setup 3, the last one we need to take a look at today. And as always, let's draw this first. Start by drawing just the meter stick and seeing what that's going to do. So, meter stick at the middle is the mass of the stick. We'll go ahead and use 200 grams again, just because it's nice and easy. This is at 50 centimeters, again, if it's a reasonably well-made meter stick. Okay, then reading some more of the information here, going through the steps that are up there above. This has at the 15 centimeter mark, which is going to be somewhere over here, a 250 gram mass. So that's at 15. Then the string is at 40, so that's going to be between these. And if there's nothing else, these aren't going to balance each other. So we've got another mass way downtown. We don't know what this is yet, so we're just going to say M, but we do know its position, so 85 centimeters. So in this question, we have all of our positions set, and we're looking for some additional mass. We need to know what's there. So we know where it needs to go. We just don't need to know how much is going to have to hang there. Okay, so we need to look at, again, torque. It's not real torque, but it'll work out for what we need going around in one direction, and then we need to see how much is going around in the opposite direction. And for this to achieve balance, those have to be equal to each other. Okay, so let's do that. Let's see where this can get. We want relative position, so find the difference between 40 and 15, and then multiply by the mass that's hanging there. Sorry, Adobe keeps trying to fix my handwriting. It's making it worse. I don't need help to have bad handwriting. All right, so looking at the difference here, this is 25 centimeters multiplied by the 250 grams that's hanging there, and then our torque adjacent measurement is going to be the product of those, which is 6250 grams times centimeters. So whatever's trying to pull and go in the other direction has to be equal and opposite to that, so we need to work through these numbers. Okay, first, the mass of the stick itself relative to the string is going to give us 50 centimeters minus 40 centimeters. So like all of these, we need the difference. Every time we see centimeters, we're going to see the number of centimeters for the string position. Everything gets compared to that. The mass that's hanging there is the full mass of the stick itself, which is 200 grams, and plus sign, that's going to combine with whatever's out here. So we don't know the mass for that part, but we do know its position. So 85 minus 40 is going to show us that it has a leverage of 45 centimeters. But again, we don't know what the mass is, so we can't make a full torque type measurement for that. Okay, but we can simplify down a bit. You just need to be careful with how much. It is a very, very common student mistake, even after I talk about it, that students will try to combine things that they're not allowed to. You need to pay attention to things like units, first of all, but then even going back to your plain algebra skills, you need to make sure you're paying attention to variables and constants, basically numbers compared to letters. It is not going to be possible for us to combine everything here because this has a variable in it. It has an m for an unknown mass, and this doesn't. We can't add these anyway, just because even though these are weird units of grams, centimeters, and it sounds like gibberish, it is not the same gibberish as these centimeters that we have on the other part. So these cannot be put together. Very commonly, students will do it anyway. They would jump and say, oh, well, that's 2045. No, for like the fifth time, these cannot be put together. So try to remember that. I'm probably still going to get emails from people who did it anyway and got stuck. But do not set those, do not add these equal to each other. Sorry, do not add these to each other. Set them equal to the other side and then solve from there. I promise I'll learn English someday. Okay, so setting these to each other for the last time. Do not combine these. It is not possible. It is not allowed. Bad things will happen. It cannot be done. But what we can do is look, hey, this thing is like this thing. We've got grams centimeters over there. And what we're doing from this is basically we're taking the total amount of torque that we know we're supposed to cancel and subtracting away the part that we already know about. And so whatever's left over here is going to be the amount of torque left over that this other thing has to make. And that is where we're going to make progress. So this difference, 4250 grams times centimeters, is equal to my 45 centimeters multiplied by the mass that I still don't know. But the good news is we don't have very many steps left. We're almost there. These centimeters can cancel with these centimeters. So now I think we can see where the grams come from. We want to get just the m here so we can divide by the number that's in front. And so that's going to tell us that this mass, it's going to have some repeating numbers in there, but I suppose it's not too much of a problem. We'll get 94.44 grams. And because in the classroom when we build these, we can only build whole numbers of grams. I don't have like half grams and quarter gram plates or 0.1 gram masses to hang and add to these. Then a lot of times we will get an answer that's a little bit further off on this one. So as an example, just so we've done at least one, let's run a percent error and see how it works. So percent error is going to set up and use a big fraction with absolute value bars. So there's a formula at the bottom of the page, but you can kind of brute force, use common sense, and figure out what it's going to be. We want to take the number that we trust more, and we want to see that twice. So from the calculation, because we've got a much easier time running the math and seeing what this is going to be, that's the number we think is probably going to be correct. We're going to test it against the random number from either from the question or that the students end up building whenever they physically put this together. So let's say as an example, a student has a 96 gram mass that they put there in order to balance. Then that's going to work itself out. We'll see some number that goes along with this. We'll multiply by 100% just to scale that up. So if we look at units, the difference between these, grams minus grams, will still be grams, but then dividing by grams will turn this into a decimal that has no units on it because the grams will cancel. If you happen to get a negative answer from this first part, then just drop the negative sign that's on there because of the absolute value bars. Then multiply by 100. If you have a percent button on your calculator, do not use it because it probably doesn't work the way you think it does. A lot of times students are doing that and they're getting thousands of percent error because they're sliding extra decimals around that they weren't intending because of whatever function the calculator is doing with that percent button. So finish running it through, get 1.65%.